Hello students, in this video we'll discuss the Sturm comparison theorems for ordinary differential equations of second order. So let's consider the second order equation. In self-adjoint form. And I'm going to look at p of x, y prime of x prime plus q of x, y of x is equal to 0. In this form of a second order ODE is called self-adjoint, and we'll see why later. Self-adjoint form. Okay. The assumptions we're going to put on p and q is we need p, where here p of x is continuously differentiable and non-negative, like so. And q of x just needs to be continuous. Okay, great. And so what we're going to do is we're going to prove the following theorem. So here's the theorem of Sturm. Okay. And what it states is the following. It says, suppose we have two solutions to this differential equation. Suppose that y1 and y2 are independent solutions to this differential equation over here. It's called star. And suppose that zeta 1 and zeta 2 are consecutive zeros of the solution y1. Excuse me. Now, what does it mean to be consecutive zeros? What that means is the following. It means that y1 of zeta 1 is y1 of zeta 2 is 0, and y1's not 0 between zeta 1 and zeta 2. And for x on the interval zeta 1 to zeta 2. Okay, like so. So consecutive zeros of y1. Then this other solution y2, then y2 vanishes, has a 0 at exactly 1 point on zeta 1, zeta 2. Okay, great. And so if you want to get a sense of why this theorem is true, the best idea is to sort of think of some simple examples of these things. So of course, the prototypical example of these things would be the case when you have a situation like this. When you had p was identically 1, so for example, you could have what? For example, you could have, if p was 1, this would be y double prime. If q was n squared, that's a perfectly continuous function, and then y is equal to 0, well then you get sine and cosine. Those are independent solutions. In sine and cosine, the zeros of sine and cosine oscillate in between. So in other words, between two roots of cosine, there's going to be a root of sine. Between two roots of sine, there's going to be a root of cosine. So this makes sense, at least for the simple example, but in fact, this Sturm comparison says it's true in much more generality. So let's prove this theorem, okay? And so the proof relies on some very important properties of second order differential equations. Here's the proof. And so the proof is that we first note that y2 of zeta 1 cannot be equal to 0, and y2 of zeta 1 cannot be equal to 0. In other words, y2 cannot vanish at the roots of y1. Now, why is that? Well, let's consider, remember that we have two independent solutions of a second order differential equation, right? If they were equal to 0, then what would the Wronskian of y1 and y2 be at that point? Let's say, for example, zeta 1. It would be the determinant of what? It'd be the determinant of y1 of zeta 1, y2 of zeta 1, y1 prime of zeta 1, and then y2 prime of zeta 1. Like that. And of course, what can we say about this first row over here? Well, if they were both to vanish, I know that y1 is going to vanish at zeta 1 by assumption. And if y2 were to vanish at zeta 1, I'd have a what? I'd have a 0 and a 0 over here, and I'd have a 0 Wronskian. And the 0 Wronskian contradicts linear independence if the functions are solutions of a differential equation of second order. That follows from Abel's formula. So in other words, that would give us a contradiction. So in other words, y2 of zeta 1 cannot be equal to 0, and y2 of zeta 2 cannot be equal to 0. So I have two non-zero points over here. So now what we do is we're going to construct an auxiliary function. Construct a function g of x to be what? To be v1 of x over v2 of x, okay? Then g of zeta 1, well, if I plug in zeta 1, I'm going to get 0, right? And g of zeta 2 is also 0. So this function g vanishes at both zeta 1 and zeta 2. And so now what? And so now, what can we say? We can now say that if, and let's suppose that to get a contradiction, let's suppose that not only is y2 non-zero at zeta 1 and zeta 2, let's suppose it's non-zero everywhere in between. If what? If v2 of x is not equal to 0 on the open interval zeta 1 to zeta 2, then this function g is continuously differentiable everywhere on the interval zeta 1 to zeta 2. So let's compute its derivative. Then g prime of x is going to be what? Is going to be bottom times derivative of the top, v2 of x, v1 prime of x, minus the top times the derivative of the bottom. Okay. All divided by what? All divided by v2 of x quantity squared. Like so. Excellent. And so now what's the idea? The idea is that I know that since g of zeta 1 is 0 and g of zeta 2 is 0, by the mean value theorem, the mean value theorem implies that there exists xc in zeta 1, zeta 2, such that what? Such that g prime of xc is equal to 0. Well, if g prime of xc is equal to 0, what does that say? That says that the Wronskian of v1 and v2 at the point xc, because what's this numerator over here of g prime? The numerator of g prime is exactly what? It's going to be, well, it's up to the error, it's the negative of the Wronskian over here. So in other words, that would say that the negative of the Wronskian is equal to 0. So I would say that the Wronskian of v1 and v2 at the point xc is equal to 0. So these conditions over here are identical to each other, right? Because the function g prime is well defined by the virtue of the assumption that v2 is never equal to 0. And since I have a 0 Wronskian, I have another contradiction to the fact that these functions y1 and y2 are linearly independent and also solve the second order ordinary differential equation. So in other words, we've just shown that if we assume that y2 is never 0 in between the two roots of y1, then there's a point in between those two roots where this function g vanishes, which will automatically imply that the Wronskian at those points must vanish as well, which contradicts the fact that they're independent solutions to second order differential equation. So our conclusion is that there must be a point that implies that there must be a 0 of v2 on this interval. So v2 has a root on zeta 1 and zeta 2. And in fact, it can only have one root. Why is that the case? So let's stop and think for a second. So if v2 had two roots on zeta 1 and zeta 2, I could apply the same argument to v2 as v1, and I would violate the fact that I have two consecutive zeros of y1. So in other words, I can play this game and intersperse or interlace the zeros of two solutions of this second order differential equation in self-adjoint form. Thank you very much.